Last time we spoke, you were talking to us about your work with blood flow. How has that progressed?
So we've progressed this work in various ways. In particular, we've been looking at designing what are called arteriovenous fistulae, which are connections between an artery and a vein made in the wrist of patients who need dialysis. These connections then allow the patient to be plugged into the dialysis machine and have their blood cleaned, replacing the function of the kidney. The challenge here is that you need a very high flow rate through this connection, but that in connections as they're formed at the moment induces significant unsteadiness in the blood flow, which is thought to cause them to inflame internally and block up and fail, which is obviously not good for the patient. So what we've been trying to do is use computational modelling tools to design shapes for these arteriovenous fistulae that retain the high flow rate but suppress the unsteadiness.
So how does that impact the patient then?
These fistulae, when they're made, in up to 50% of cases can actually inflame internally and then fail, and then the patient has to have new surgery to open it up again or another fistulae made, so it's time in hospital. It's not good for the patient experience. There's also a cost burden for the medical care system. So being able to stop this failure mode in our case we're looking at an implantable medical device to form it into this optimal shape, could have a range of positive impacts.
So you've had an article in the Times. How did that come about?
So we recently published a journal paper in Physics of Fluids detailing a lot of our recent results on the arteriovenous fistulae work, the optimal shapes that we came up with for the devices, fabrication of prototype devices, preliminary preclinical testing results.
You must be quite happy with that.
Yeah, very happy. It's a nice piece of publicity, so
yeah.
It's good.
So what other applications through your work on these fistulae can you expand on?
So there's various other applications of the technology and of the optimal shapes that we came up with. One example would be in coronary artery bypass grafts. Perhaps this is where surgeons have to go in and bypass an existing blockage so the blood can get around. So there again you have to make these artificial connections between blood vessels, and if we've identified shapes that optimise the flow patterns so they don't restenose and block up again, that could be useful in that situation.
Have you used any interesting techniques in achieving these shapes?
Yes, so we've used the simulation tools from the aerospace industry to actually model the flow, but then we've coupled that with machine learning algorithms. We actually trained a machine learning algorithm. We said, okay, you have to satisfy certain constraints, like the device has to fit inside a patient's arm, and it came back with a design. So this is quite, I think, an innovative use of machine learning, which is being deployed across a range of sectors at the moment in the medical space, and it's exciting for the future really as to the opportunities there.